Hello, Fosdan. I'm Riccardo Binetti, and today I'm going to talk you about Astarte, what it is, and what we built with it, and why I think you should use it. So, first of all, some things about me. Uh, I'm Riccardo Binetti, also known as rbino online. This is my website, GitHub page, Twitter, etc. I'm a cloud specialist at Secomind in Padova, Italy. And I started out there as an embedded Qt C++ developer, but now I'm almost full-time developing in Elixir. So why delivering data is not enough for an IoT project? So IoT may seem like an already solved problem and an overused buzzword, but it actually not. Because there are some aspects of IoT which are still open and are not usually handled properly by the existing platforms. So first of all, authentication. So many platforms just ask you for a username and a password or don't even bother to do that. So basically any device can act as any other device and publish data for each other without any kind of control. Then there is data modeling. So many IoT solutions don't force you to declare the shape of data. And this is very fine to start out because you say, oh, okay, I can send any random JSON on this platform and it will digest it. But it actually takes away guarantees from your system because when you want to have an integer and you instead receive a string, then there is some kind of mismatch that you can solve without having some structure in the data. And you can think of this as the difference between schema and schemaless databases. The other problem that many solutions have is the one-size-fits-all approach, because usually IoT platforms are shiny dashboards. So you say, okay, I want to see my data graphed and I want gauges and graphs and so on and so forth. Okay, nice. But when you want to build something with your data that is not what the default frontend is showing you, it gets hard really quick. And so what Astarte is trying to solve is also this problem by exposing data by API instead of widgets. So which are the results of all of this? Usually each new client, each new person who has to build its own IoT platform, instead of adapting an existing one, starts to roll their own. And there is a lot of reinventing the wheel. Smart devices are not so smart and they are taking over quickly. And if everyone implements its own IoT platform, possibly buggy and so on, when the singularity happens, you won't be able even to put your shoes on to run away. So let's introduce Astarte. Astarte is an open source data orchestration platform focused on IoT. So the approach that Astarte uses is that we know that everyone has slightly different requirements for their IoT platform. So there are different device protocols and different applications that uses the device data. And Astarte tries to solve this by focusing on the common building blocks and make it easy to integrate custom stuff you might need. What are the components that make up Astarte? Astarte itself is a set of microservices which are written in Elixir, and it's made to be modular and replaceable if needed. So each microservice is replaceable with your own implementation if you need. And it's designed to be Kubernetes native. Then there are devices SDK that cover a lot of different use cases. So we have SDKs for Qt5, C on ESP32, Go, Java, Elixir, Rust, Python, JavaScript, you name it, and much other SDKs are on the way. And then there is Astarte Flow, which is a separate project from the Astarte microservices, and it's a data processing framework focused on reusable blocks and pipelines. So let me introduce some of the Astarte concepts which can be useful to understand all what we are doing inside of Astarte. First of all, how we model data. Interfaces. Interfaces are what are the data modeling primitive we use in Astarte. So there are JSON files, and a device usually supports multiple interfaces, and it declares its capabilities when it connects or when a new interface is added or removed. Interfaces can be shared across different devices, so you have uniform data access between different devices implementing the same interface. The interface versioning adheres to semantic versioning. This means that if a device supports a 1.0 interface, the 1.1 interface can only implement a subset of the operations which are allowed in the interface update. And this makes sure that all devices with a 1.0 and 1.1 interface are compatible with each other. And the API that is generated for a device is derived from its interfaces. There are some properties of the interfaces. The first is there are two different types: Datastream and properties. Datastream are stateless ordered stream of data. So you can think of it as sensor samples, commands, events. So all values are registered. If you sample a temperature, you now say it's 20 degrees, then in a minute it's 21 degrees. All these samples are saved in the database. While properties are stateful, synchronized state with no history. So if you're just interested in the current state of the device for a specific thing, then you have to use a property interface, and actually only the last value is saved. And properties have the implicit guarantee that that just the correct last value is saved. So they are implicitly sent with QS2 on MQTT, for example. Here you can see an example of an interface, of a JSON file of an interface. Here you can see the interface name, the major and minor version, and the type. So, for example, this is a properties interface. The ownership is another important aspect of the interface. Can be either device or server. Device interfaces are the ones which where the device publishes the data, while server-owned interfaces are the one where the server owns the data. So with Astarte, it's possible to both receive data from the field and send commands to the devices, and all is described with these interfaces. As you can see, an interface contains an array of mappings. These are rather minimal in this example, so you have multiple endpoints, and if you can see, you can also have parameters inside the endpoint. So with this interface and these mappings, you can represent the humidity and the temperature of multiple rooms by changing the room ID when you send a message. And each endpoint is mapped to a specific type. So the usual types are supported: double, integer, long integer, string, datetime, binary blob, and their corresponding array version, so double array, etc., etc. And inside mappings, you can also have additional properties, like, for example, you can define the database TTL, so a value can be saved in the database only for a limited amount of time if you want. or you can define the QS, which is used to publish the data on the device side, and some other properties that you can find in the Astarte documentation. But basically, this is the most minimal example you can think when thinking about interfaces. And the semantic versioning I was talking about earlier basically means that if I do a new minor version of this interface, the only thing I can change is that I can add new endpoints. So the devices supporting the 1.0 interface still are compatible because they are just not going to send data in a new endpoint for the new endpoints. But I can't change the type of endpoints, I can't change the type of ownership and so on. So I can guarantee that they are compatible. Okay. So on the credentials management side, we have the pairing component, which is the component dedicated to emitting and renewing credentials. It signs SSL client certificates, which are used to perform SSL mutual authentication with the MQTT broker when the device connects with it. And all the SDK just take care of this in a transparent way, so the user does not have to care about credentials renewal or requesting it. It just gives the credential secret to the SDK and it performs all the needed operation. How does the pairing flow work? So you have the agent, the entity that is in charge of registering devices, and it registers the device and obtains a credential secret. This operation can happen either during manufacturing, so you ship out devices which already have the credential secret, for example, burned in an OTP, or directly on the device. So we support both use cases. After that, the device has this credential secret and it exchanges this credential secret with actual credential. In the SSL mutual authentication case, the device sends a certificate signing request and pairing API returns a signed certificate to the device, verifying that the credential secret the device sent is actually its own. And device credentials can and should be short-lived, and because the SDK just renews it for you, so you can have a very short-lived certificate and don't care if the device gets compromised. Another important concept inside Astarte are triggers, which are a way to perform an action when a specific condition is met. So basically, triggers are JSON descriptions, like interfaces, but this way, instead of describing the shape of data, they describe some condition and some action. The currently supported actions allow to send HTTP requests or publishing a message to a RabbitMQ exchange. So you either have a webhook on the webhook which receives the HTTP request on the other end, or you can have an application which consumes from a RabbitMQ queue, and you can use that to receive filtered data, because you don't receive all the data coming from Astarte, but just the one that matches the condition, and act on it. So you can populate your application backend. You can use Astarte Flow, as we're going to see later. You can. The important thing is that this acts as a funnel. So you just have a subset of data you're interested in, and you can react to it. Here you can see an example of a trigger. As you can see, you have a trigger name, and you have here are the conditions, which are expressed as an array of simple triggers. Right now, we are not yet supporting combining simple triggers with the complex operations, but it's on the roadmap. So here, for example, you're defining that when incoming data, when a data is received on this interface with this interface measure on this specific path, so you can, if you recall from early, the room ID was actually parametric, so you can match on specific instances of the path. Then you send a post to this URL, and this allows you to react to specific rooms receiving data. But there are also additional conditions. So you can also say, for example, for numeric values, you can say if it's less than some defined value, or if more than, it's greater than, or you can match string values, and you can also define you can also check if a value is contained in an array. So you can pretty much have a very fine-grained control on what data is passing the trigger condition and triggering the action. So the outermost part of Astarte are transports. And the responsibility of a transport is converting incoming data to the Astarte internal representation, which is BSON and INQP metadata, since all data flowing inside Astarte passes through RabbitMQ, and the transport gets the data coming from the device and translates it to this format and delivers it to RabbitMQ. Currently, we provide an MQTT transport working with the available SDKs out of the box. It's implemented as a VernMQ plugin. It has mandatory SSL mutual authentication, and the protocol is well documented, so you can roll your own compatible SDK. So if for some reason we don't cover your use case with our SDKs, you can always take the protocol and roll your own SDK. Or you can provide your own transport. So for example, if you have an existing application which just sends a plain MQTT data, you can always write a different VernMQ plugin which translates that data to the Astarte format. So this is another reason, another way we offer some more flexibility for our users. So I'm going to talk to you about the Astarte components. So all the microservices which are effectively making up Astarte. Here you can see an high-level view of the components. So all user-facing APIs have an API suffix, as you can imagine. So there is AppEngine API, Housekeeping API, Realm Management API, and Paying API. All API services except AppEngine API have a corresponding backend service, and actually this communication between services is passing on RabbitMQ with an RPC protocol, and so basically this is done so that users can actually replace any of these services if they adhere to the same RPC protocol. Then there is Trigger Engine, Data Plan, which is responsible for the data ingestion. And here there are the transport which communicate with RabbitMQ. So now let's see each service a little closer so we can understand what each of them does and what it's used for. So first of all, as you saw in the previous slide, the main database which is used by Astarte is Cassandra. all data is stored to it, and we also support ScyllaDB as a drop-in replacement for Cassandra. If you don't know it, basically ScyllaDB is a write of Cassandra in C++. So it has some pros with respect to Cassandra, and we support both of them. The tables, so the structure is not static, but the tables are created based on interfaces, and data can be made explorable using Cassandra's TTL. So when you install a new interface, Astarte takes care of actually creating all the tables which have the right shape to store the data for that specific interface. And this means that there is not a general way to store data, but it's specific and optimized for each type of interface. So the first component in the hierarchy is housekeeping, and it's basically the super admin interface. So you use Housekeeping API to create realms and delete realms, and basically that's it. So what are realms? Realms are the multi-tenancy token of Astarte. So each realm is completely isolated from the other, because they use different key spaces on the database, and the key spaces in Cassandra are basically the equivalent of database in usual SQL databases. And Cassandra and Astarte was designed with multi-tenancy in mind. So we have also as the service deployments, you can use it to deploy a single instance with multiple users using different realms, which don't interfere with each other. And that's what realms are. Housekeeping is used just to manage them, create them, etc. Realm management is the main administration interface exposed to the user. And as user, we intend the administrative user of a realm. And with realm management, you basically perform all the operation to set up a realm to receive data. So you install interfaces, you install trigger, you can manage realm configuration, and perform all the administrative operations. And realm management has an API and a backend like housekeeping. Pairing API is the part we described before. So it's the component which is responsible of everything concerning device credentials. So you have two subdivisions of the API. There is the agent part, which is the one used to register the device, and then the device part, which is the one which is the only API of Astarte which is targeted by devices and not by users. So devices use it not only to obtain the credential, but also to obtain information on their transport. For example, the default transport and the default SDK query paying API at boot to ask the URL of the MQTT broker. So you can also change the URL of the MQTT broker, and the devices on the field will just accept the new one because they always ask for the broker URL. And using pairing API, it's also possible to inhibit devices, preventing them to obtain new credentials. So if you have a device which is not, which you think is being compromised, you can inhibit it from pairing API, and that device won't be able to request new credentials anymore. Database plant is the core component to ingest all the data coming from the devices. and it's called data updater plant because for each device, a data updater being process is spawned for every a being process is spawned. So a being process, if you're not familiar with Erlang and Elixir, is we can see it as a green thread. So it's not an operating system process. It's a lightweight process, and the fact that each device spawns its own process, which is responsible for delivering data, means that if a single process or a single device is able some way, because of course there are the checks in place, is able to send malformed data that crashes the process, then only that process crashes and all other devices are left unaffected by this. So there is a strong guarantee of isolation, not only between different realms, but also between devices inside the same realm. And data updater plant is also able to communicate with the transport. So the transport send data to data updater plant, but actually data updater plant is able to send data to the transport. So it is possible to force device disconnection when malformed data is received. So if you combine that with the device inhibition, then you can make sure that a device that is behaving badly can be disconnected as soon as it starts to send rogue data, and it can also be inhibited so it can obtain a new certificate to connect back. Data updater plant is also responsible of verifying triggers conditions and notifying trigger engine. So since all the data flows from data updater plant, conditions are verified there, and all data is guaranteed to be delivered and saved to the DB in the same order it was delivered to the transport. So this was we designed Astarte with the intention of guaranteeing in-order delivery. So from the SDKs to when the data is saved to the database, we want to guarantee that if you send ABC, then you will save ABC in the database. And this is especially important in the properties case, because since you just saved the last value, you have to make super sure that you save it in the right order. Otherwise, your state will be out of sync between the device and the cloud. So trigger engine is another component, and it's the component responsible of executing the trigger actions. Actually, just the HTTP action, because the publishing on AMQP happens directly inside the data plant. And it performs HTTP requests when a trigger condition is met. And the event can also be enriched with additional headers defined in the trigger. So in a trigger, if you, for example, if you want to send a webhook on an authenticated HTTP endpoint, you can also add, when you install the trigger, you can add, for example, an API key or some kind of authorization header. And each time a trigger is executed, the event also includes that additional HTTP headers. AppEngine is the component, is the API that is used to retrieve data sent from devices and to stream data towards them. So AppEngine is the core of what your application will interact with. So basically it exposes device information, so you can query a device, see if it's online, offline, its introspection, how much data it's sent, etc. But then under the interfaces, it also exposes a REST tree, which is dynamically built on the interfaces that declare is on the interfaces that are declared from the device. So the API always reflects the current state of the device. So it if the device is supporting just the temperature, then under /device/device ID/interfaces, you will only find the temperature interface, and you will only be able to query that. But if the device at a later time says, okay, I also support geolocation interface or humidity interface, then they will be added at the moment to the API, to the device API. So you can always query the data, just query the data that the device supports. And the other role of AppEngine is, of course, allowing the data flow in the other direction. So if you send data, you can send data using a post request, and the data will reach the device using a transport. So you just do a post request, and Astarte takes care of delivering it using MQTT with the correct configuration. And another nice thing about the AppEngine is that it exposes not only a REST API, but also a WebSocket API, which is based on Phoenix channels, which is Phoenix is the web framework of the Elixir language. And it's built on top of trigger mechanism. So you basically can create a room and you subscribe to specific volatile triggers. So the trigger I showed you earlier, you basically use that kind of configuration to see, okay, I'm interested in this channel room. I'm interested in receiving the data for the temperature interface for that specific device, or the humidity interface for another specific device, only if it's more than 60% humidity, etc. And you basically listen to that room. It's a pub sub. So when a trigger condition is met, an event is streamed to the room. So you can have a room with multiple triggers that receive live updates, and you can use that to have applications which show real-time updates coming from the device. So how is all this authenticated? All APIs are authenticated using JSON Web Tokens, but Astarte is not responsible of emitting them. So we just define a specific format, and we accept JSON Web Token signed with a specific public key. What is the specific public key? Basically, when a realm is created, you install the public key of that realm, and when you perform requests on that realm, the public key is used to verify if the JSON Web Token is valid. And inside the JSON Web Token, the authorization is expressed using a combination of regular expressions matched on the path and allowed verbs on that path. So, for example, this claim says that in Astarte AppEngine API, so AEA, this JSON Web Token is able to perform GET requests on /devices, whatever, /com example temp and humidity, whatever. So this means that with this JSON Web Token, you can query the temp and humidity interface for all devices. This is a regular expression, so you can put a specific device ID here, or you can put get and post, so two verbs, or you can get very sophisticated with it. And this makes it possible to decouple user management and using a dedicated tool for that. So in Astarte, there is no concept of users, because we just accept JSON Web Tokens and we delegate the token emission to someone else. You can, for example, use Keycloak for that. So the RabbitMQ RPC is the internal plumbing of all services. All components inside Astarte are connected through RabbitMQ. The RPC protocol is defined using protobuf schemas, so you can adhere with it. If you want to rewrite your own realm management API, you can do so. And outside of that, because Astarte Flow is not connected to all the other components, but it's actually a separate project from the core Astarte microservices, there is Astarte Flow, which is, as I told before, is a data processing framework based on reusable blocks and pipelines. You basically, Flow allows to process data in a streaming fashion, and you can use Astarte connected devices as source or as a destination, but it's not limited to that, because you can also use other types of sources and destination, for example, HTTP, plain MQTT, AMQP, and the block. The nice thing about Flow is that you can specify a container image that is managed by the Kubernetes the Astarte Kubernetes operator as a block. So you can have, for example, an Astarte device that publishes data and passes inside your container image that, and you just have to implement the algorithm, and all the plumbing inside is taken care of. So you just receive messages, you apply your algorithm to it and say, okay, I'm done with it. And you can basically implement, you just focus on your algorithm without having to take care of the plumbing. So the deployment of Astarte happens with Kubernetes. Astarte is designed to be a Kubernetes native application. All services are containerized using Docker, and all our production deployments are running on Kubernetes using our Kubernetes operator. So we have an help chart to install the Kubernetes operator, and you just after that you just define an Astarte custom resource and install it. And the operator takes care of deploying all the microservices I showed you earlier. In the main Astarte repo, there is also a Docker Compose-based deployment, but it's mainly oriented towards testing Astarte, because on your local machine, it can be a hassle to set up a Kubernetes cluster just to test out Astarte. So if you search for Astarte in 5 minutes, we have a tutorial which makes you deploy the Docker Compose based deployment and start having fun with it. And on the monitoring side, all Astarte services exposed Prometheus metrics, and future versions will also include integrations with the Prometheus operator. There are some clients for the Astarte APIs. So we have the Astarte dashboard, which is a web-based client written in TypeScript, which is used to interact with all Realm APIs. So it has the sections to interact with Realm management, so you can install interfaces, install triggers with very useful graphical editors. And you can interact with pairing API, registering devices. You can have live updates on the devices, so you can see data flowing, which is interacting with AppEngine API. And this dashboard is deployed by default in clusters. Or you can use Astarte CTL, which is a command line interface written in Go. And Astarte CTL can do basically all that the dashboard can do, minus the WebSocket interaction, of course, and or can be used also at the higher level of deploying an Astarte cluster. So it has some also some commands which interact with kubectl. So, but the core thing is that both these tools are actually just using the Astarte REST API, which is exposed to all users. So you can just roll your own tool. They don't have any special access to Astarte. They can do whatever any API user can do. So I will show you now some use cases of stuff a couple of use cases of stuff which uses Astarte. The first use case I will talk about is Edgehog. So Edgehog is a device manager, a device and fleet manager, which is built on top of Astarte. So this is the latest project, and it's open source too. So it's already on GitHub, and it's heavily under development as I speak. And all device operations are implemented on top of Astarte. And there is the cloud side and the device side. And on the device side, an Edgehog SDK, which is built on top of the Astarte one, is provided to simplify development. Right now, we have an SDK which can be used on ESP32 devices. But we already have planned to build future releases which will cover Linux using the Rust SDK. And the backend of the Edgehog exposes a GraphQL API, which can also be used by third-party clients. So the nice thing about the GraphQL API is that you can just query the data that you need, or you can query multiple devices. You can perform operation on multiple devices in one go. And the front end of Edgehog interacts with this API and allows you to perform all the operations easily. So like the Astarte dashboard, the Edgehog front end is a graphical way to do all the operations that you can do interacting with the Edgehog API. So how does the Astarte integration of Edgehog actually work? All the devices which are connected and want to use Edgehog and are using actually the Edgehog SDK use a well-defined set of interfaces, which you can find in the repository. So this makes sure that every device which is using that interfaces is actually an Edgehog compatible device. So you don't have to use a specific device or a device for a specific vendor. You can also roll your own device, and actually it can also be not an ESP32 device. The important thing is that you implement and you use those interfaces, and you'll be able to use Edgehog with it. And data coming from the device is queried using Astarte AppEngine API, and there are also some triggers which are used to update, for example, the device connection status. So as soon as the device connects, the status on Edgehog changes and the device is marked as online. And the commands and OTA are pushed with the Astarte AppEngine API send feature. So you basically send post requests to AppEngine API to send data towards the device as usually. What are the features right now of Edgehog? As Astarte, it's thought to be multi-tenant by default. So you can already have multiple users which are independent from each other because they map to different Astarte realms. Then you can have a device hierarchy based on hardware models and appliance models. So these are concepts we introduced to decouple the specificity of a specific device with and abstracted abstracted. So, for example, hardware you can think of hardware models as different revisions of a specific PCB. They all map to the same hardware model, because if you have the same CPU, then the code is going to run in the same way, even between different revision. But of course, as soon as you have a revision which moves out GPIO to another pin, then it's going to be a different hardware model. And appliance models, on the other hand, are what the device is used to. So for example, if you have the same hardware model, the same board that is used for a bike sharing platform, and you have some boards which are on bikes and some other boards which are or e-scooters, then the hardware model is the same, but you have different appliance models actually. And all this classification is useful because then the device can just declare a part number, and it's automatically classified between with its hardware model and its appliance model. And all this classification is also useful because because it helps the OTA process. So right now we have implemented manual OTA, so you can push the device. You can push an update to a single device, loading it on Edgehog. But the planned feature is to have update channels which automatically roll out updates based also on appliance models and other models. So you can't push an update to the wrong type of device because all devices are classified under this hierarchy. And some other features which Edgehog exposes is geolocation and reverse geocoding with different strategies and providers. So you can see where your device is using the Wi-Fi scan, the Wi-Fi net it sees, the hardware GPS sensor, and so on. And you can map the coordinates to a specific address. And then there is telemetry, so you can expose battery status, OS info, SIM status, and all the basic information you expect to have for a fleet management tool. And then you can send commands to the device. For example, you can control the network, or you can blink an LED to identify it in your when it's between other devices, so you can identify a specific device you're working on. And basically that's it on Edgehog. And another interesting use case that we worked on with the Oniro team is the Oniro integration. So Oniro is an Eclipse Foundation project, and it's an open source distributed operating system, which is targeting IoT devices and trying to defragment the development for embedded systems. So the idea is that you can run it on different hardware for different makers, and it should run always the same. And it uses the same build system for different kernels. And the talk just before mine was on Oniro, so if you want to have some more information on that, either you already have watched it or go rewatch it. And the interesting thing is that the Astarte SDK can be integrated as a bit-baked recipe in the Oniro, and it has been packaged in Oniro using bit-baked cargo. And it's going to be included in Oniro's next release, Goofy, on the Yocto Kickstone branch. So this is a work in progress too. So here are a couple of links where you can leave some feedback. But this means that you're going to be able to connect to your Astarte instance using Oniro, and that's a great thing. So here are some references. You can go on astarte.cloud, and here are all the website links for the Astarte repository and the Edgehog repository, and the documentation. The Astarte documentation goes very deep inside all Astarte concepts like interfaces, triggers, and so on. And now I think we have about 10 minutes for the Q&A. So thanks for the attention, and let's pass to the live version of myself.
Talk. There were some questions in the chat. So one of our listeners asked, there is a big emphasis on interface versioning. Could you please make a practical example on how it is used?
Yeah. So basically, the idea is that we emphasize interface versioning because this way devices in the field can be updated gradually. So if you have some device in the field that gets updated and starts using, for example, a 1.1 interface, it can start to send data on new endpoints, while the other devices can continue to use the old version on the interface. And this makes sure that you don't have to update all devices in one shot, and but at the same time, all devices can still use the shared triggers, because triggers are installed to a specific name and interface measure tuple. So more generally, we guarantee that all data for a specific interface name and measure version is uniform, and so we enforce the rules for minor updates to ensure that if you have a device that exposes a certain interface with a certain measure, you can expect data to have that shape, even if maybe it's missing some subset of data because, for example, the device is using an old version. But at least you have the guarantee that the shape of data is the same, and you can write applications that query, for example, APIs, and you know that that shape of data will be there.
Okay, cool. Thank you. There was also a follow-up question from the same user. So does Astarte have a web front end, some graphical interface, dashboard, and stuff like that?
Yeah, actually, we provide a dashboard mainly for administrative tasks, so installing interface, triggers, and so on. But since we understand that in the beginning of the project, you don't already have your front end built to be attached to AppEngine API, using Astarte dashboard, you can also do some basic data querying. So you have a devices list, and if you click on the single device, you basically can see you can use the WebSocket interface, and so you can see the data flowing into your device live as it gets there. So you can use it for the initial testing of your application, because you can query data in interfaces and you can see live data coming in, so you can debug that at least the device is publishing data correctly. And then after that, basically you can build your application. And another interesting thing we can have, when you don't have written your own application yet, is that we provide a Grafana data source. So you can there is a Docker image of Grafana with our own Astarte data source. So you can spin up a Grafana instance and show data from your device using Grafana. So this is for everything you have to do before writing your own application, and when you don't have yet something to connect to the Astarte API.
Okay, cool. I think that's really helpful for people who are interested in using that. So I do not see any more questions in the chat, but I have my own one.
Okay.
So you mentioned something about the certificate rollout for devices. I've been curious if you are using your own CA, you have your own implementation, or you're using some other open source project to deal with that.
Yeah, we are using another open source project, which is CFSSL. which is a Go component made by Cloudflare, which is basically a CA service exposing an HTTP API. So basically, when the device requests a new certificate, the operation is that the device sends a certificate signer request, and the pairing component passes this CSR to CFSSL that signs it basically and sends it back to the device as a signed certificate. So this is the default component which is included in Astarte, so you don't have to build your own CA and manually manage all of that. But the fact is that this, again, is something which is pluggable. So we try always to provide an escape hatch. So when you install the on Kubernetes, when you install Astarte on Kubernetes, you can always provide an alternative CA certificate. So you can either use the integrated pairing API, or you can decide that you will have your own pairing mechanism, and you will provide the certificate to the devices in some other ways. And we allow to do that by providing an alternative CA, and the broker will just verify the certificates with that alternative CA.
Okay, cool. So maybe one more question also from me. I've been curious, how well does Astarte scale? You mentioned about having, a separate beam for every device, and obviously it all runs on Kubernetes, so it's probably auto-scaling, right, and stuff like that. But what's your rough estimate on the amount of resources that we need to deploy Astarte to serve, for example, 1,000 devices or something like that?
Well, for 1,000 devices, I think you can do it with a simple cluster with like some machines with about 8 gigs of RAM and a bunch of vCPUs. So your standard Kubernetes production cluster. But we have the deployments with hundreds of thousands of messages per second. So it scales very well. And the cool thing is that it scales well with the hardware. So if you need more devices or more messages per second, it's really easy to add another node to your cluster and just grow the resources defined in the custom resource that are dedicated to Astarte, and Astarte will take care of using all the resources in your cluster in a nice way, and it will scale well with the cluster size.
Okay, cool. Thank you very much. If anyone has any more questions, feel free to join the dedicated room for this talk, and I'm sure that our speaker will be happy to answer them.
Sure.
Thank you once again.
Okay. Thank you. Bye, everybody.
Bye-bye.